I'll just start until Stefan is ready. So hello and welcome everyone to our talk. I hope not every one of you was already in Amsterdam. If so, we are sorry. Yeah. So that's Stefan, my colleague. I'm Andreas. I'm senior software engineer at Innovex GmbH. My day job is microcontroller programming, and I also do a bit of product owner jobs. We were in the same company before, so that's where this pet project started. Specialty of Stefan is more security testing and software architecture. But in this pet project setup, we want to show you how we developed a full product with Zephyr. He is the guy who's writing the software, and I'm more in the perspective of the hardware engineer, because most of the time I'm finding the hot end of the soldering iron. And so cool. Please go ahead.
Thanks. Just introducing myself. I'm Stefan. I'm from UL Solutions. In case you don't know us, we are like we're like the TÜV, but actually it's the other way around. TÜV is like UL Solutions. Do testing, inspection, certification of hardware and software. I'm more the software security guy, doing some functional safety, some cybersecurity. And you're here for, and unfortunately, I think it's too small to see it, for this small device here. It's not that complex. You can press a button here. It makes a nice sound, blinks some LEDs. And the big question is, well, why do you listen to us for half an hour now, which is, kind of not that interesting. And I think Andreas will now tell us why it maybe still is.
Yeah, so our agenda is a bit split up in three parts. One thing, the first part is some planning. Then we will show you how we do a proof of concept style product, and then we, like we do it in professional environment. So maybe you figure out some key points in your daily adventure when you're in the hardware software development life cycle. So hope you have some fun. So first of all, what do you need to develop a product? Well, you first need a problem you want to solve, or even better, you invent your own problem, your solution, your product is the perfect solution for, right? And let's call it vision. So our problem, at least one of them, is first, formerly we were in the same company, and we had a problem. There was this really long hallway with lots of offices in between. And so when I wanted to go to the coffee machine, the staircase over here, so Stefan was right next to the staircase, and the coffee machine was in the first floor. So I wanted to notify my colleagues that I wanted to go and drink some coffee. And I also wanted to get notified if these people in the front are just leaving and you don't tell me. So what are the options? Going around and telling everyone want a coffee, or sending direct messages in Teams and hope you don't forget anybody, or some group chats. We all know them. We just mute them as soon as we get invited to a group because they are annoying most of the times. Cat videos are most of the time quite funny. So we thought we need another solution, something technical. So our vision was, hey, we are all in the team IoT, so let's build a thing that does a job for us, notifying everyone. So we wanted to have an independent system, because we don't want to force people installing software on their computers, corporate IT, and maybe some of you know the pain. So we want an independent system, broadcasting, hey, let's go drinking some coffee, but we want to interrupt people, but not to be too annoying, so that people are switching it off and then get disconnected from the whole coffee group. You also can drink tea, but we just call it Coffeecaller. So we wrote up some requirements because at least we are engineers, right? These devices should be basically on all the time. So one key aspect is that we have low power consumption, as it is a pet side project, and we don't want to inflict too much costs on the company, so it should be very cost efficient. Should support some sort of mesh networking, because putting bunch of devices into a Wi-Fi and corporate environment. Then corporate IT is again at your side, and what are you doing there? And of course, as Zephyr is a great project and we wanted to try it out, we are looking something with great Zephyr support. So we went to our cupboard and grabbed some of our well-known Nordic NF DKs and tried out the Bluetooth mesh sample. So one thing the mesh sample is doing for you, when you press one button at one board, it blinks the other blinks one LED on the other board. And then we did some range testing, and we found out, well, the ranges, the coverage is enough for to reach at least every other office. So when we plan to put one Coffeecaller in each office, then the mesh working will be fine, right? So it's time to build our first prototype in the proof of concept phase. We defined our minimum viable product as we want to have one button, one buzzer, and because it's always fun, some RGB LEDs. We want to have it USB powered, so that we don't have to put up complicated power supplies. And we wanted to have Bluetooth mesh for the start. And then we thought, what is cheap, what's available, and then we came across the ESP32 dev kits, so not the fancy new RISC-V ones, but the very old extender Tensilica ones. You can get them for very, very cheap on some AliExpress sites. So all I did is basically I designed some carrier board where I can just put this dev kit on, and well, I like some pin headers if I want to experiment, so I put all these free pin headers there. But the main product is just the buzzer in the middle, the green big button where people can know where to press to start a coffee call, and basically an RGB strip on the top notifying, hey, there's someone who wants to go and drink some coffee. Yeah, so it's the basic prototype, and that worked quite well.
Yeah.
But we also have to develop some software, and that's where Stefan comes into play in this project.
Yeah, and I'm going to tell about our software development process, if you want to call it a process, because while Andreas did all the hardware, I just looked into Zephyr and thought, okay, what do I need? I kind of knew Zephyr before, so I know, okay, there's a lot of things already there, there's a driver there, but also things that are helpful, like a state machine framework, for example, so I don't have to write it myself. So I looked into the Zephyr code, into the sample code, find out the right kconfig options. Previously, it was like, okay, I need to code like 20% myself and need to find 80% of the right kconfig options. I think that even is a bit too less or too much right now. Copied it into my application, make it compile again, and start with the next thing. And so I added a machine framework, I started the button interaction, the drivers for the LED strip, and everything else that is now on this small board that we showed you right now. Unfortunately, just copying software is not software engineering, and copying software does also not lead to the best and safest product. So in the end, while it worked, it got a bit messy. Let's be honest. So everything lives in app. We at least had headers and source files separated, but there were just a lot of things just laying around. You see it. Everything is a flat hierarchy in source. There are no tests. There are some boards with some definitions that Andreas wrote when he was finished with the hardware. But in the end, it was working, but from a software perspective point, it was not great. Also, when it worked and we deployed it out in our great office we had before, we got some customer feedback. Because while our ideas were great and they worked pretty well, we have several issues. So suddenly some boards stopped working. So Andreas activated a hardware watchdog that just restarts. We also noticed that sometimes the mesh decided that on this one wall it was a bit thicker, it just kind of stops working. Some people complained that the buzzer is too loud, others say the buzzer is not loud enough because they are in meetings the whole time. But also from our point, the project setup, wow. The project setup was kind of, I would say, unprofessional. Yeah, it was hard to really develop the software as we want to have it. We also needed to have the hardware around, which, well, I waited until the hardware was finished, which worked out. But especially the mesh thing was discovered to be a bit of a problem. When we updated to another Zephyr and another HAL version, suddenly this Bluetooth mesh stopped working. So we contacted Expressive and said, hey, I think you broke the BLE Mesh support in Zephyr. And they were like, what do you mean with BLE Mesh? BLE Mesh was never officially supported in this kind of hardware. So we had one of two commits where the mesh just worked, and other things were broken, unfortunately. So we were kind of unhappy with that. Additionally, but that was majorly Andreas' problem, it needed manual soldering, which the hardware guy does, obviously. But also from the abstraction layer, it was more like a shield for already a shield, which we noticed on a meetup that we both had in Erlangen. So we decided to go into the next phase, which we call the professionalism phase.
Yes. And are some people of you doing Scrum in their daily life?
Oh, God. Tobias is unhappy.
So we decided to do it better because we are still engineers. So for our hardware, we decided to wanted to have a compact PCB. We want at least I didn't want any through-hole components because then the board is wobbling around on your desk, and I don't like that. And we also decided to go for an SoC with good Zephyr support. And we wanted to have a USB-C port because, unfortunately or luckily, micro USB is dying out slowly. So there is no the three-way plug-in of your USB header. And also for the software side, we wanted our software to be compatible to native sim so that we can write some tests. Also, we wanted to have everything as a subsystem or at least a library so that we can split out things and reuse components we already wrote for other projects, or at least to test them individually, and also do some automated testing some officially supported way of communication between the SoCs. So how did we select our components? There are a few things to consider. First of it, the SoC support. Second, the driver support. For the RGB LEDs and the sensors, because in our office it got quite hot in the summer. So I decided to put a temperature sensor on it so you can create a heat map of the building. And you have to decide if you want to solder it by hand or let it manufacture as a whole thing. And of course, the price tag, it's still a pet project, some nice gadget, so it shouldn't be that expensive. What we chose was a NRF 52840 SoC because we made some good experience with it on the development kit. We also went for a full PCBA manufacturing because I chose a QFN package, and that's a bit hard to solder by hand. For those who don't know, that's some ball grids, so you can put your soldering iron between the PCB and the chip. So you need to have some way of reflow soldering to get it properly soldered on, and then some X-ray inspections because you can basically not look under it if it's soldered correctly. And we wanted to have some higher production volumes that it's not feasible doing it by hand in the evening and soldering all the boards. So the first iteration, that's where the agile part starts. How do we start developing some hardware? So I'm no hardware engineer. It's just some things I taught myself and experienced over time. I chose a form factor as a credit card and didn't just cut it off to have it square, nice and tight. I have an RGB strip on it, some buttons and buzzers, one 3-pin header or some 3-pin headers because I like to reuse those nice boards as some development kits or play around with it. A quick connector, that's basically an I2C extension a standard where you can just connect different breakout boards and have some fun with the I2C. And of course, put a 10-pin SWD port on it to flash and debug, because there's no on-chip programmer there anymore. And then we have some feature creep. It's agile, right? So you take your hardware design and show it some people, and then they say, well, looks really nice, but yeah, can we make it in the shape of a coffee cup? And some extra buttons and GPIO LEDs were also really nice. And then you go back to your KiCad and do some moving around of components, adding some stuff, and then you came up with this nice little board, and then you think, hey, fine, all the requirements are met. Then you go back to your product owner or your product management team and show the final solution, and then they say, yeah, can those LEDs be in a rectangular shape? Because I do some trainings with it, and then it would be really nice if they are not in a row, but in a rectangular shape. And also, more 3-pin headers would be nice. And I also use some servos in my training. So can you please put in a bit more connection features? And also, what about NFC? I thought the Nordic SoC has some NFC capability. Can you put a connector for it also? And then, go back to your computer, move around some components, and then you have this little nice board. Gets quite crowded at the moment, so no more space left for more features. And then your product management team is, what about mounting holes? Because some people want to mount it to some board, and then you look at it, well, where should I drill some holes here? Because, yeah, but I don't want to screw it up. So, of course, I moved around some components, and as the mounting hole diameter wasn't specified, I choose some M2 screws, and they fit quite nicely over there. So yeah, I managed to squeeze in 3 more mounting holes, and yeah, I think people are quite familiar with some agile and hardware development. So at the point you show it to some other people, then they are like, oh, can you do this? Can you do that? And yeah, that also happened here in our pet project, right? So, and now, as we have the final hardware, we can start coding, because before it wasn't possible. At least it wouldn't be possible if we haven't Zephyr. Because what Zephyr gives you, and that's the really great advantage over some proprietary software development systems you have used before, is called the device tree and all the subsystems, because this is an abstraction layer. As Stefan stated in the beginning, we started with this board. I wrote some drivers and interfaces to get the button working, and also the RGB LED strip and the buzzer. And I put some sort of semantic call over the already existing drivers, so that the user who writes some application can just register callback to the button, or just say, hey, buzzer, do your beep 3 times, and don't have to provide some PWM things on their own, or just set some RGB LEDs. And yeah, when I developed this new board, and Stefan was finished with all the refactoring, I asked him, oh, well, what's left over from my code I initially wrote? And he said, basically everything. He just copied it over, and it worked. So, wrong direction, sorry. So once you have your device tree in place, with all the interface defined in the device tree, you have your semantic call laid out for your application. You can just put your application on top, and then it really doesn't matter which board you have beneath it. So you can just start write your application code. When you have some development kits, switch between hardware. Really doesn't matter which chip you use, at least. If you have the features on the chip you want to use, like some 2.4 gigahertz radio that supports openthread or BLE Mesh, and that's one big thing that difference differentiates Zephyr for me from all the rest of the development process, because I've never seen it before, and it's quite complicated with magic to do that by hand. Yeah. And as I talked a lot about software and application, that's the point where Stefan kicked in and cleaned up basically all the source code.
Yeah, thanks, Andy. Yeah, even I was surprised. He asked me like 2 or 1 weeks before the open source summit and asked, hey, what did you need to change? And I was like, wait, I didn't change a lot of your code. I thought you did already. And I was quite surprised how good Zephyr is at just abstracting this away. I was also surprised when he told me that there are actually 4 servo motor drivers now on the Coffeecaller board, but I accepted it. Okay, so I could have just kept the software as it is, but for several reasons I was unhappy with my work. And the first one, and I pretty much think that is a best practice that I would also do in my commercial work, is always have a native sim emulator available. So if you are not familiar with it, a native sim is a POSIX-based board which brings the application to a runnable state on your laptop. It's really an emulator, and there's a bit of things behind it, but generally it just makes it executable for a normal Linux system, which is great. So I do not need to always flash it on the board. I do not need to wait until Andreas has again finished another hardware layer or another hardware iteration. I can just have it testable on my on my system. So the first thing is, okay, I want to make it compiled for native sim, and as we did not expect it to retouch this code ever again, the code was not directly able to run on it. Classic example: this board, as you hopefully see here, has an LED. This laptop does have an LED, but I can't really control it. So while we already worked with node aliases, you see the DT alias on the right side with the LED strip, it just does not compile as the native sim does not directly provide it. So what we did is there is this overlay capability in Zephyr, and we just everything the native sim does not already provide, we just add it part by part until it is compiling. Yeah. So there are some great things and some great abstractions where you can just replace your real hardware component with a compatible emulator, or even something that just works similarly. For example, the watch step that we added, or Andreas added, then the real board has an NRF watchdog as it's based on an NRF board, but Zephyr also provides a counter watchdog which just counts up a counter and notices you and breaks something blocks. So this is the good part, where you just need to find, okay, where is the proper binding that I can use in my code? But there are also things that are still, unfortunately, not in Zephyr. I'm working on it. Please trust me. Which is, for example, the GPIO, the LED strip drive. So there are a few different ones. We have a VS 2812. And there is nothing that just compiles in some form of proper emulation behavior that I can check. So instead of just selecting, I actually need to write my own emulator if I want to have it compile and do something useful. So I just put the fake LED strip there, created a device tree binding, and also just wrote the proper code, which is, once you have done it, quite easy, because you just put the driver code, first the bindings in the DTS bindings LED strip folder have a very, very, very small YAML. That is the whole YAML, because I just decided I take the base LED strip YAML and do nothing else, because it already provides color mappings and length and everything that I was expecting to be there. And then you need to do a bit of C code. Majorly, you need to provide what is this file compatible with. You need to define some API. This is for the LED strip quite easy, as there are only 2 commands: update RGB and give me the length of the RGB, which is quite similar, and copy the proper definition and for each loop from any other LED strip that's already there, because this part does not change. So while it was a bit cumbersome at first, in the end, I only needed to do 2 drivers myself, and the rest I could just deactivate or have a drop-in replacement. So this was one way how I make it possible to compile also for native sim, also play around with it and have some form of behavior checks without needing to flash on real hardware, which is also great for CI. Second, but way easier, was this HAL folder. So we had at least the whole hardware abstraction in a subfolder. For example, our buzzer Aldrin was in this small subfolder, and I do not want to have it in my Coffeecaller app themselves. So we just took it as it is and moved it into this small library folder for the source files, or the include folder for the .h files, which was not only great because I wanted to reuse that also for my temperature Coffeecaller, as it got quite hot in the building again, but also because I think that's the better place for these kind of things. And especially one can finally also test part of that on a lower level without manually checking if the LEDs are on. So what I did was also doing some integration testing on a very small level. So I took that is my C, or the interesting part of the C file contains of the buzzer that's available over an alias, and some timer that also when I press the button somewhere, or when it starts buzzing, someone needs also to stop. And I wrote now some tests that properly check if it works approximately as expected. These all run on native sim, which is fine, which is great because timing is not a real issue on native sim. So when there is 300 milliseconds, it really will be 300 milliseconds emulated. So I have determinism that I maybe not have on a real board. So for example, my tests are just, okay, I want to buzz my Aldrin shortly. I'm going to check if my fake mock call is properly doing, and also if it stops after my given seconds, because the default was 250 milliseconds at start. Okay, so I abstracted the Aldrin at least, but there's still some source code inside, like, for example, the state machine framework, the whole BLE Mesh communication network that we also switched out by side. And what one of our colleagues, ex-colleagues, told me, okay, a good application has nothing inside beside a main that is quite empty and a lot of kconfig things. One can discuss if this is a good idea. We tried it and it worked out quite well. So the first thing is I want to introduce a Coffeecaller broadcast system. So when I have different subcomponents, for example, not only the Coffeecaller, but also the temperature, they all can do some pub sub mechanism, just put in messages, and afterwards, receive messages they describe them. So it was a bit of more work also because I moved from BLE Mesh to openthread, and this was better and officially supported by more boards. But as you can see, I also did something else. I took care the emulation of the chip. The BLE chip was quite hard, and therefore I decided to be a bit tricky here, and also have multiple different transport layers. One for openthread for the devices, one for BLE Mesh if I want to have it, or also one that is just running a local queue where multiple other devices can subscribe on. I've solved the selection over the KiCad mechanism. So at first, okay, do I want to have the subsystem at all? And then which transport layer do I want to use? Do I want to use openthread or local queue? Also some defaults for the boards I want to support. And also in the CMake list, link the one or the other source file into it. And after the CC broadcast system, it does not end, obviously. Yeah, I, in the meantime, also implemented the CC temperature subsystem, which tells me that it's really hot in the summer in the building with numbers. But also the whole Coffeecaller mechanism, the whole state machine things got into our own subsystem, which select the broadcast one. The state machine get reflected out, the kconfig variables, for example, the buzzer tone got reflected out. And yeah, in the end, what you see at the lower right is pretty much everything that is now living in this app Coffeecaller folder, which is really just this main that does nothing, and the kconfig variable which starts different subsystem in the right order with the right priority. And therefore, the whole application got a composition of smaller subsystems that I can selectively enable or disable, depending if I'm really interested in specific features, for example, the servo motors. And with that, I have another thing implemented in this time that is what I think is also great for subsystems to test them interactively and checking if they work out, is providing a shell interface so you can just send simple commands, call simple functions without triggering a button press externally. So while this board would ring when I press and test it this way, this is kind of not very fun when I do it again and again in my office room. Turns out it is a bit annoying. So what I do normally is, okay, I prepared native sim the whole time. I'm just putting in a subsystem shell so I can not only communicate with the real board with it, but also with native sim. So I implemented some very simple commands which simulate the real hardware behavior, which is, for example, hey, CC subsystem, press a button or receive a kind of message. And especially the nice thing on this whole shell thing is the test cases for it get quite nice because due to some recent changes, there's a shell harness where you now can just put in these commands in test case YAML. They will be executed. Twister will take care of it. And you get response if your system, based on output, behaves like you would have expected it. All right, and with that, I go back to the hardware and what we learned about the way. And
So basically, lessons learned. It's all there in Zephyr. You just have to find it. And also, native sim is the key for fast iterations and testing. And one thing I didn't mention was that you can have this iterative hardware approach in Zephyr. So you don't lock your software development features while you are creating the next iteration of the hardware, because everything you have to change is some device tree options. And what you also can verify is with all these dev kit boards that are available, if you have something like this LED strip here, which is looking quite funny at the moment, then you can think like, there are boards where the LED samples were working quite right, but on my board it isn't. So what you also can do is with all these sample applications that are there, just try it out, flash it. If the sample is not working, then maybe it's some fault in your hardware. And if the sample is working, then you have a bug in your software and have to take a closer look at it. So that's also one big advantage you have when you use the whole Zephyr system instead of the classic bare metal development you did before. And basically that's it. Thank you for your time. As mentioned in the beginning, this whole project is open source. So if you want to have a look at these KiCad files, how I designed this board, then you can go on the left side, follow this QR code, have a look in the KiCad hardware layout designs. And if you are more interested in how this whole software development project is working, how do I set up some test infrastructure, then Stefan did a lot of work on his GitHub project. So on the right side, you can find the whole Coffeecaller application with all the subsystems Stefan just showed you. Have a look into the GitLab CI or GitHub Actions workflow, how you can set up your pipelines for your project. That's it. So a few minutes left. If you have some questions you want to ask right away, perfect. Just in the middle, go ahead.
Earlier you mentioned that your software development was blocked because of the hardware changes, if I understand you correctly.
Yeah, well, so in theory we could have developed simultaneously, right, the software and the hardware, but maybe I just said it wrong. So we were not really blocked.
That was my point, because you can work with different board versions, for example, and start the development of the application based on board version 1, and during this software development you can change the hardware, and then you just say, okay, use board version 2, and everything is working out of the box if you do it right.
Right, and what I just said, if you don't do it right, then you can do some.
Exactly.
Then you have some regressions between your hardware versions, and then you can.
Hardware takes, in my opinion, hardware takes a lot more time than software, because you have this long waiting cycles for PCBs. Every time.
Exactly. Yeah, and that's exactly what you mentioned. You can develop the application simultaneously while you do your hardware development, but because we were in different projects all the time, so we just did it on our free time. So maybe I just said that wrong, but you can definitely go for that approach, and that's something I really want to highlight, that this is different. And here's another question.
Yeah, so you mentioned that with the Zephyr RTOS, you can abstract away the CPU, like you know vendor stuff in the way.
Yeah.
And it means you can use any CPU.
What?
So you kind of said it means you can use any CPU. It doesn't matter, right? Any run Zephyr RTOS. Yeah, once it's.
Yeah.
How do you pick which one to use in that case?
So for the NRF, we just went for this NRF SoC because they were just lying around in our office. So we just go to
we just had them kind of.
Yeah, we just had them and just played around with it. And that's it. We also had some ST boards laying around, but they don't have any.
It's only pretty Nordic in the
especially in the. We had some history with especially Bluetooth Mesh over the last years.
Yeah.
Don't ask too much details, but in the end, it was always okay. We have these NRF boards, and especially for the whole Bluetooth, for the mesh parts, for the connectivity things, they were where we know that these will, with a high chance, just work. So we went for it. There's probably another CPU which some more sense or less sense or something that's better, but we just went a bit safer here, and we're quite.
Maybe to answer your question, how you select your hardware components, I would recommend to. If you want to say, I want to have some temperature data collected in my. Huh?
Yeah, I was more wondering, I guess, the point I was getting to. Do you think people would end up choosing, it would just be the Zephyr C processor at some point, that if kind of everyone just uses one generic CPU that's become the thing? And
no, I think the different silicon vendors have their own selling points. So some are more like in the medical safety critical applications. Nordic is more in the low power, long range Bluetooth thing. So it just depends what you want to do in your application. And then my recommendation is, if you have set up your requirements, so what you want to do in the product, then go into the Zephyr source code and look for examples and drivers that are supported. Go and buy the development kits and just play around and look how it worked out. I think we had one more question, and then
we can.
It's also okay. Like now we have from 7 to 7:15. We have the break time.
Yeah.
So if you have questions, you can directly ask it to them.
Maybe just one more question in the back, and then it's
a small one.
It could be either a short or a long answer.
Oh,
yeah.
It's a two-layer question. So the first question is, did you play around with Rust within Zephyr, either in this project or in some other one?
In other.
If yes, how was the experience?
It depends.
I make it short. We did like start of the year, end of last year. We did that. My expression is also a talk from the Open Source Summit, which had, in my opinion, the same expression. For this size of project, you pay a lot of glue code and pain to make it a bit abstracted and have some type-safe application logic that just works and is safe and great. You have some C code from Zephyr, which is also great. You have this more or less big glue code layer, and you will put a lot of bugs and a lot of misses up in there. So in my opinion, it's right now not really worth to pay this bill, as you need to tweak a lot of things here. The build time is suddenly so much bigger, and I mean, it's so easy to mess up this small layer because the two systems handle things just completely differently, and you will still have memory issues and other things just because you don't know how the other side exactly is working.
Yeah. But at the moment, the whole Rust lang support in Zephyr is a one-man show, if I remember correctly. And at some point, you will have some unsafe statements in your Rust to jump into the C code, and the line, the border, where you want to draw this line, that's not specified yet. So that is floating. Yeah. So that can be very high level up in your application, or very low level in the driver. But then basically you end up rewriting Zephyr the whole way in Rust, and so that's floating at the moment.
It's just not ready yet, but good.
No, it's. I would not recommend using it in production. Or you want to save your job. That is also. Or you want to save your job, then this is a great possibility.
Okay, then thanks. I will call it an end. Have some pizza.
Thanks for listening this long.
Yeah.